So this here is going to be our fourth and final example from the Simple Harmonic Motion Review. Again, I recommend taking a minute here, pausing the video, and trying this question on your own. It's definitely the best way to check if you are understanding, is to try them on your own and compare your answer with what I get. So in this case, we've got a gorilla swinging on a rope who is observed to reach a maximum speed of 5.5 meters per second. So let's write down what we know. Their length is 20.0 meters. The speed is 5.50 meters per second. And we want to know what the maximum amplitude of the gorilla's motion is in degrees. So how far does the gorilla swing when it reaches its maximum amplitude? Anytime with a question like this, where we are dealing with a velocity right away, or a speed rather, anytime you should immediately think this is going to be a conservation of energy question. Conservation of energy. So the two types of energy that are being transformed into each other in this question, well, we have gravitational potential energy, and that is going to be equal to kinetic energy. So as our gorilla swings, when the gorilla is right at the equilibrium position, this is where our kinetic energy is maximized. So at this point, all of the gorilla's energy is in kinetic form. When the gorilla reaches its final position, it has swung over to here. At this point, we have our potential energy instead. And we aren't going to have any kinetic energy left because the gorilla is going to stop once it reaches its maximum amplitude. So we can say that these two types of energy are going to be equal to each other. Let's start with the potential energy. Gravitational potential energy is always going to be equal to m times acceleration of gravity times height above a reference point. So looking at our little diagram here, there is going to be our height. And this is going to be equal to, kinetic energy is 1/2 mv squared. Right away, we can notice that we have a mass on both sides. We weren't even given the mass in the question, so that's a good hint that it doesn't matter. So our mass is actually going to cancel out here. So since we're looking for this amplitude here, we'll call this theta. That's going to be related to the height. So let's start by figuring out what the height that the gorilla reaches is. So we'll divide both sides by g to isolate the height here, and we find that height is equal to 1/2 v squared over g. There's no indication that this is on any planet other than Earth, so let's go ahead and assume that g is 9.81 meters per second squared. Not sure that we've ever discovered gorillas on a different planet, so let's go ahead and assume that. So our height that we find is 1/2 times 5.5 meters per second squared divided by 9.81 meters per second squared. And if we calculate this out, we can find that that height there is going to be equal to 1.54 meters. Although, of course, that's not what the question was asking. The question was asking what is the maximum amplitude of the motion in degrees. And this is where I like to draw a couple of triangles in a more careful manner. So this length of the rope here, we know this length is equal to 20 meters. When the gorilla has swung out to the side here, this length is still going to be 20 meters of this rope. The length of the rope isn't changing. What does change is that we now have a height above the ground, which we said was 1.54 meters. So what we can do with this information is we can create a little triangle here. And this is going to be a right angle here. So in order to find this angle, we can use some trigonometry, some of our trig identities, to say that this length right here on this side of the triangle is going to be the difference between 20 meters minus 1.54 meters. I'll call this H2, let's say. So H2 is going to be equal to 20 meters minus 1.54 meters, which we'll say is 18.5 meters. Don't worry, I kept all my decimals when I did my calculation in my calculator. So now we've got a triangle, and again, let me just draw this out. So this triangle here, I'll draw it over here. We've got a side with a length of 20, a side with a length of 18.5, and an angle in between. So if we think back to SOHCAHTOA, cosine of our angle is going to be equal to adjacent over hypotenuse, which in this case is 18.5 over 20 meters. So our angle is going to be the arc cos, or I'll just write it like this, cos of 18.5 over 20, and so that angle there is going to be 22.6 degrees. So the tricky part about this question is figuring out these sort of triangles at the end, so keep that in mind.